Hello, this is video 33. In this video, I'm going to talk about centripetal force, just the basics, and then in the next two videos, I'll go over a lot of examples. So in the previous video, we talked about centripetal acceleration. We said whenever something was moving in a circle, then that means its velocity was changing because the direction was changing. So there was an acceleration that we call a centripetal acceleration. So now we just take it a step further and we say, well, if there's an acceleration, then there must be a force. Forces cause acceleration. So we're going to call any type of force that causes the circular motion, we'll call it a centripetal force. So the direction of it will be toward the center, just like a centripetal acceleration. And we can rewrite Newton's second law now. Newton's second law has been written as a sum of forces equals ma, and that was for linear motion. Well, now that we're doing circular motion, the acceleration is going to be replaced with a centripetal acceleration, which we said was v squared over r. So Newton's second law becomes the sum of the forces equals mv squared over r. A very important thing to note is that the centripetal force is not a separate force. There's always going to be one or more forces that are causing your object to move in a circle, such as tension, friction, or gravity, sometimes even a normal force. It's a force responsible for the circular motion that we give it the name centripetal force, but it is not a separate force. So if we look at this picture, I usually do a demonstration in my classes where I swing a ball in a horizontal circle, and I go in front of the students. I say, okay, now I'm going to release it. Where is it going to go? And often the students are a little bit scared and think it's going to hit them in the head. But it just depends how good I am at releasing the ball. So if I'm swinging it in a circle like this, a clockwise circle, and the students are right over here, so this is all the students over here, well, if I release it when it's right there, then it's actually going to go this way, and it's not going to hit anyone. Now, if I release the ball when it's right over here, then it's going to go that way, and yes, then it might hit somebody. But the point is that when I release, then I get rid of the tension. The tension is what was causing it to move in a circle. When I get rid of that tension, then that object goes off in a straight line. So you can see how the tension was responsible for the circular motion, and thus we would call this tension the centripetal force in this example. Let's do a few your turns to get the basics, and then we'll be done with this video. So this is similar to what I just talked about here. We have a puck that is tied by a string to a stake in the ice. It's swung in a circle. What force is producing the centripetal acceleration? So hopefully you can see that the answer is E, because the tension in the string points this way. We learned the tension always points away from the object, right? We're looking at this puck that is undergoing circular motion. So if we got rid of this tension, it will go off in a straight line. So that means the tension was providing the centripetal force. It was providing the centripetal acceleration as well, right? If there's a force, there's an acceleration. Let's do one more. A coin sits on a turntable as the table steadily rotates counterclockwise. What force or forces act in the plane of the turntable? So this thing is rotating counterclockwise, and for some reason the coin is not slipping off. Right? If there were no forces causing the coin to go in a circle, the coin would just go straight off, just like the puck. So if it goes in a circle, there must be at least one force that's pointing toward the center. So we can get rid of choice E. There has to be a force if you're moving in a circle. So which force is it? So choices B and C here say that there's a centripetal force going toward the center. That's never going to be our answer. Centripetal force is not a separate force. We have to look at one of our familiar forces, and that's the one that's causing that circular motion. So between choices A and D, they both have the static friction force pointing toward the center, and that's kind of counterintuitive, but really that's the correct force here. That static friction force is preventing the coin from slipping, so it's keeping that coin stationary. Now, is there a kinetic friction force? Well, there would only be a kinetic friction if it was actually moving relative to the turntable, but it's still relative to the turntable. There's no kinetic friction. So the answer is A. So in the next few videos, we will go a lot more in depth with the centripetal force and actually solve problems. But for now, the important thing to remember is you have to look at which force or forces that you know about that cause the object to rotate, to move in a circle. And that's the force that's going to be called the centripetal force.